So just heads up again. I'm sure there's no data loss, but Program IZ Pro is currently not bringing up our playgrounds. So for those of you who may be working on Lab 7 using a Program IZ Pro, you might feel like you lost that. I think it's going to come back. I'm having the same problems pretty much. I can't see any of my playgrounds at the moment. So we'll find out more, but don't panic. Just kind of hang with that process for now, and I'll have the typical forgiveness for technology when we get to our kind of grading on the weekend on that stuff. We'll figure out where we are on that. Today, oh, sorry, today we're going to talk about two things. One that's just a nice thing to have. I will never test you on this because the syntax is so crazy, but it's a really nice feature to have. It's another overloading of a symbol. So if you remember when we overloaded plus symbols, we taught our classes how to add themselves together. But there are lots of other symbols out there like the less than, or the stream insertion operator, as it's officially called, for cout. So we can teach our classes how to convert themselves into a format that can be printed. And that is super, super helpful for debugging and other things, which we will see today. We're also going to talk about this concept called templates, which is like almost like another mini language all by itself. It's very cool. It's a concept that exists across other languages. So Java has something called generics, which is kind of like templates. So it's a very powerful thing. Well, we'll dig into it when we get there, but just a little more syntax we got to process. So we had our lab 7. Lab 8 is optional today. All of our optional labs stay open until the end of the semester, so you can always come back and finish them at a later time, and they will replace your lowest lab grade. So no pressure on that. You can prioritize on your tic-tac-toe, which you should be doing. And we have Monday off, even though we don't have class Monday. You guys shouldn't come into class for any other classes. And then Tuesday, of course, our quiz is due. It will not include lecture 8. How did I goof this up? It should have 7 on there. So it should be 4, 5, 6, and 7, but not 8. So we don't have 8 today. Okay, just so you know. And I think I cover what those things are on this slide, right? Prototypes, default arguments, a lot of stuff that probably you already knew: pass by reference, pass by value, constructor initialization list. So just a kind of a catch-all of all of the stuff that we've talked about so far. Okay, so you want to maybe take that early for a throwaway test, and then kind of come back and hit it again. So hopefully that stuff uh, is stuff that you have retained since our last couple lectures. So another reminder about homework 2, and a little real life story about this. So I know I've kind of told everyone I want you to standardize on the meaning of R and C here. So the values that are received by your take turn method from main and from my unit tests are going to be in the range of 1 to 3, not 0 to 2. Now, I know you can get your code working and convince yourself it's good from 0 to 2, but I am going to test it in the 1 to 3 range. So really, you want to be aware of that. Please try to adhere to that so we don't have to have a back and forth. So, that should be the lower right corner in a 3x3 tic-tac-toe, right? Not 2-2. So, and the reason I stress this is because it points out what I think is like a deficiency in kind of our computer languages. So it'd be really cool if the data type for that int r could also come with a range. Yes, it's an integer, but it should be an integer within the range of something and something. That would be really cool for a language to support that as a sort of a metadata or some other runtime checking system. Might be an expensive thing to do, but it'd be pretty good. The reason it would be really important is the NASA Mars Climate Orbiter was lost at the cost of millions, billions of dollars, because it was sent the right types of data, but they were metric instead of US standard. And so it just sort of, flew off into oblivion and burned itself up in orbit somewhere. So it's not just about the data type is the moral here, but it's also the range that we quote unquote agree on that we're going to actually adhere to. So heads up on that for your homework too. Okay, so really lightweight. Will not drag you through all this. The moral of the story is to have lots of developers and lots of separate CPP files. We need to adhere to this somewhat crazy system with .h's and .cpps. And our include guards allows us to do that. And the pragma once will probably preserve your sanity. Most companies these days and most compilers do support the pragma once. In some senses, it's a lot less buggy than the other one because we don't have to worry about the underscore naming and all that stuff. But you can use either. And certainly, I'm sure there are places like Google and large companies that are a little more hardcore about this and want to just stick with the if and def, define, all that good stuff. Okay. So I know many of you are still in the throes of agony over Lab 7. So hang in there. Once you kind of get through that, I think you'll be kind of oriented to that issue there. Okay. So that is our include guard. So for today, we are going to be doing operator overloading. So this is like cout. When I say cout and a variable name, cout knows how to print an integer and it knows how to print a character, but it does not know how to print an instance of a blah, whatever it is, a banana, whatever your class is. Cout doesn't know how to print it unless we teach your class how to be printed. In other words, how to convert itself into a string. So if I have a class that represents a car and I want to do a cout of that, I'm going to need to overload the less than operator inside of that class to teach the class how to be printed. So we don't teach cout how to print the class. We teach the car how to be printed by the cout. Okay. And so that's the overloading of the stream operator. The other thing we're going to talk about today is this idea of adding different data types. So, well, not adding different data types, but writing 2 or 3 or 4 versions of a function so that I can do things like add different data types. So here we see 2 different functions, one that adds characters and one that adds integers. And maybe one produces an actual concatenated string and the other one produces a number. So normally we got to write those versions ourselves, every possible one that anyone might ever want from our add function, which can be rather tedious. But templates give us a way to let the compiler do that for us. So templates are kind of like clones that are automatically created by the compiler. So here we have one sheep function that adds 2 characters, another one that adds 2 integers. And so we could define these things manually, right? But what if we could have a pre-compiler, kind of like that preprocessor we talked about with the pound includes and everything, but a little bit smarter, that goes through our code and says, oh, I noticed that, you are trying to add 2 characters, so I'll write a character version. And I noticed that you're trying to add 2 integers, so I will write an integer version. And that's what templates are. It's a preprocessor or a template writer that looks at your templatized code and also the code that you kind of just use down below in main, so to speak. And it says, oh, looks like you're going to need some of that stuff. And it goes ahead and writes it for us. And then we don't even really see those things. They're kind of behind the scenes somewhere in our translation unit. And it feels to us like we just didn't have to do stuff. So there's like this magic hand, really, that's kind of looking at our code before it actually creates the executable and figuring out what it's got to write, which is kind of creepy, I know, but it's memorable. So we've done it before. So here's our vector int nums. So what is that? So we're saying, hey, template writer, I'm going to be working with a vector of integers. And it kind of goes, okay, let me go write that for you. So it literally is writing an entire version of vector library for integers for you. So now if below that you have a vector float, it kind of goes, oh yeah, I got to go write that one too. So it's literally writing all of that code for you, and your program is getting bigger as a result of just having 2 different kind of vector variables in there. So the preprocessor looks at your usage to decide whether or not to write something or not. That's one key takeaway. It's not just going to write every possible flavor. It's going to look at what you're doing kind of in main or whatever and kind of go, ah, I see you need one of those things, right? So what we want to learn is, how do we do this? We want to write our own classes and our own functions that can be expanded that way automatically by the compiler. So in order to do that, we're going to kind of do this overload first, because it's going to help us kind of follow the journey along the way here. So let's take a look at this. Again, optional material, but we'll use it in class to kind of help us debug. So here we have x equals 10. The value is x, right? So we're using that insertion or binary operator to sort of add this on to what was a blank chain and then add this on to that and on and on. So that connector that we've used for many years now, many of us, is really just a binary operator that's adding something on and then pushing it out kind of to our user at the left there, okay? So what we want to do is overload that operator so that we can actually have our entire instance printed out, whatever that actually means. Like if it's a car or a person, we can kind of decide what that is. So we're going to teach our class how to do that. And so what we would like to be able to do is something like this: create an instance of a person and then see out the person. Okay, so before we've always said j.printme or j.print description or j.get string and then see out that string. So what we're doing here is we're just throwing the instance of the class added, and it should be able to figure that out. Okay. So that's the idea. And it's really useful for debugging. So here's a 3D point where I can just say, see out P. And now I should get a really nice parenthetical description of my 3D point in space. Okay. So we're going to build that into all of our classes. And that's just going to make debugging easier, but it'll kind of come up with a useful application with our templates as well. So let's take a look at our point3D class to start. Okay. And remember that, just review, our constructor initializer list has 1 colon, right? Easy for our fingers to jump into the double colon after lab 7, but that's just our 1 colon. And then we're just assigning those values over there into the X, Y, and Z, okay? So that's kind of a reminder of what we're doing. But we also want to add a couple things to our class real quick. So we're going to quick add that plus operator. Adding two 3D points together would be just like saying, I will take all of yours and I will add them to mine. And I am the this, right? So remember that our new value is going to be, the value of one thing but plus the other, right? So this is just the number, not the 3D one, sorry. So just reviewing our good old friend, the operator plus that we did before. So we want to apply this to a 3D point, okay? So that operator plus is just our binary thing. So take a look at this if you can or if you want. So just to challenge your mind a little bit before you, hit the quiz on Tuesday, right? So here's what we want to do, right? So just think about, what is it that we want to return from this? I want to return a point 3D, right? Capital, and I am going to create an operator plus method, and the input to this thing is going to be a point 3D, and I'll just call it right-hand side, okay? And so I want to return a new point 3D. So the quickest way to do that, if you want the shortcut, is to say return point 3D, point 3D, 3D, and I'm going to add together these two things, right? I'm going to add together my X, right? So I have to notice that my constructor needs 3 things, right? So I'm going to add my X plus the right-hand side's X dot X, right? And my Y plus the right-hand side's dot Y, okay? And my Z plus the right-hand side's Z, okay? I'm sure I got some syntax errors here, but that's me creating a new instance and returning it, right, on the fly, okay? So let's just see if I got past that part. Of course, I missed the semicolon on line 30 down below. So it looks like this is, where did I do that? Constructor, operator plus. Feel free to shout out if you see where I did it. Pair together after class. Huh, all right. Expected call. Class different. Oh, I'm missing a curly brace. Missing a curly brace there. Thank you. Oops. Okay, but not that. Not that. All right. Well, I won't waste all of our time with typos here on the screen, but hopefully you guys, for the purposes of remembering how we do this, there we go. Okay, so we got our operator plus in there, etc. So let me just cut to the chase, right? So here's our kind of operator plus added in there, okay? So we can create a temporary variable or we can just do it directly, okay? So that's our step one for operator plus, okay? So, and this is optional. Just remember that this is a pointer. So when we need it, we use the arrow in there, okay? So optional in this case, okay? And then we just saw that implementation there. Now in main, when we're doing this, we're creating our instance. So we're going to want to print this instance here in just a second. So I want to know what sum is, and I don't want to have to do this mess out here, right? I don't want to have to do all of this every time I want to do cout. I would just like to say cout sum, right? And have it do that for me, okay? So the stream operator lets us do that, which is really nice. And this is how we use the stream operator. So this is how we would use it for the number class, our abstract little number example. So first off, we got to declare it a friend to the OS stream operator, okay? So we say friend, we say that we're returning an OStream ampersand as a reference so we can chain things together in a long way. There's our overload. Instead of operator plus, we have operator less than less than. And what we're receiving, although we might not realize it, is we're receiving what stream we're working on plus the thing that we want to glue into that stream, okay? So it could be anything. It could be a number, a point 3D, whatever, okay? Now this little extra mojo over here makes things go fast. A const reference, as we will come back and review a number of times in this class, is a special way of avoiding a copy of this thing. Since I just want to look at it so I can print it, there's really kind of no point in making a copy of it. So many advanced C++ developers use const and ampersand in this way. It's not strictly required. It just makes things go a little bit faster. So you could just say number RHS, okay? Like so, okay? So that's what we're doing. We're taking the existing stream and somehow extracting some printable information, okay? So you can see what we did in this case is we just dressed it up. We said, oh, whatever you are, add on a parenthesis, and then pull the value out of that thing and then glue on another parenthesis, okay? And that is really all that we need to do, right? To update that stream, okay? Notice there's no cout there. We're just sort of augmenting the stream. And then we're going to return that thing, right? So that somebody else can chain something onto the end of it, okay? Kind of a lot of syntax. I always forget it. I always look it up or double check it with some code that I've written. So that's why we're not going to really worry about testing you on this thing. But we are going to throw that code into a lot of our classes because it just makes it a lot easier to debug, okay? So let's look at what we're going to do with our other class. Well, I'll show you the solution code for this, but this should help you out. So we want to add a new method to overload this thing, okay? And we want to return its name, right? So that's really, or sorry, the operator minus minus is the name, right? So we're going to return some basic information like, 1, 2, 3 on that, okay? And then we want to just print that thing directly, right? Cout sum p plus p equals some sum, right? Okay, so let's take a look at this in the solution. Here's our kind of goal in our main area, right? So cout what p is, or cout p plus p equals p plus p. I mean, look at this. We're actually overloading the plus operator at the instance level. It's figuring out what that is, giving us a new result back via our overloaded plus operation, and then feeding it into our OS stream conversion to give us the nice parentheses that give us the answer to that addition. That's a lot of cool stuff that's coming kind of for free in Cout because we overloaded those two operations inside of our point 3D. Okay. So let's take a look at the code for that. But this is really what that's going to produce. And that's some really nice code to write. I'd much rather write that code than having to do all the things to pull out the, getters and setters and all that stuff to just get that thing to print out. Okay. So here's our point 3D with our constructor, our operator plus overload, and our stream overload in there. Okay. So we're really just saying, hey, this is what I want to see come out for P anytime somebody tries to print P. Okay. I notice that the P is not coming from this. It's coming from the outside. So we're just sort of adding this to our class as part of the package, right? As part of our point 3D kind of class package. Okay. A very nice feature to have, a little hard to remember, but really helpful, especially when we're debugging stuff. Okay. So it's going to let us just see things much, much more clearly without all of the mess. It's essentially the same as a print me, but we're fixing it up so that it is actually going to go directly into the Cout stream. Okay. So that's just one trick. And we'll come back to that reference thing, which is kind of cool. It just allows us to chain things together like this, right? So we can kind of do those more complicated stream outputs. Okay. All right. So enough with that. We want to get on to the main event, which is really understanding these templates. So again, templates are like a preprocessor. We have to remember they do not happen at runtime. They are part of compilation. So what happens is we're getting a lot more code with a lot less work. Okay. So essentially, we've gotten used to passing in values into our functions, but we are now going to pass data types into our functions, more or less. But we're going to be doing it at compile time, not at runtime. Okay. And it's going to save us from needing to write overloads, right? All these different flavors of stuff we would have to write, the compiler is going to do it for us. And it's going to kind of do it after it does all these includes, or if it's part of the process of doing those includes. Okay. So our code is going to get much bigger if we need it to, if we use a vector int. So just loading the vector library doesn't mean it's going to expand it. It depends on how you use the vector library, which is really cool. And we've seen this before, right? Vector int, vi, vector string. So this is like warning the compiler, or actually in this case, we're not loading it. We're actually literally telling the compiler, hey, I need you to go write 3 different flavors of this, okay? So it's kind of looking through though and going, okay, I got some work to do. So I'm going to go write that thing right now, and it'll tuck it into our code, and we don't really have to worry about that. So that is what the template system actually would do for us, okay? And again, in other languages, similar things, generics in Java is what it's called, okay? And it just makes our code cleaner. Let's take a look at how that system works, but we will for sure in this class see lots and lots of these things, string, vector, list, a deck, map, sets. Those are things we're going to look at here in another week or so and dig into all those nice additions to C++ that came in the last 10 years or so. Okay. So let's start with functions because they're definitely simpler than classes. Okay. So simple example to start with. I have two types of functions. Get the maximum of A and B, right? Which we could all write, right? We have char arguments there, and we return a character, or the get max of integer. So tedious to write all of this stuff. So what we want to be able to do is just sort of call the function and have it figure it out which one of these things it needs to write and then call it, okay? Without us having to do the actual work. So really it's just function overloading that we're talking about. And the only difference in our functions is, of course, the data types in these two functions. Not every function can be written automatically via templates, but where the only difference between your functions is the data types, that is a great candidate for actually what we say templatizing a function, okay? So here is how we actually do that. The first thing is we start out our function by coming up with a fake name for a data type. I'm going to just call it Q. A lot of people call it T, but I'm just trying to be different because for a long time I thought it had to be called T. You can call it anything you want. So I'm going to say getMax is a function that returns type Q after receiving an argument A called Q and an argument B called Q. Okay. And that's it. So this is a templatized function. It is not executable, and C++ does not know what to do with that. It would just completely barf with that unless the preprocessor writes the correct version for us. But how does the preprocessor know what to do? Like this. So this is expecting one template parameter. So just like vector int, my function now has a templatized category there. So I'm saying, hey, I am calling a character version of this templatized function, and I'm giving it 2 characters, which makes sense. So the compiler preprocessor is going to come in and see that and go write that version, and then it's going to see an integer version, and it's going to go write that one as well. Okay. And only because we're trying to execute the function in that way. So I really am calling a function here. It's like, hey, go get me whichever of these is bigger and return it. And oh, by the way, it's this, right? So maybe most of us haven't dealt with templatized functions as much as templatized classes, but they're definitely out there. Okay? So that's really all we're doing. Okay. It's like, hey, find the Q's in there and replace them with char, and then write another version for int. Okay. So the preprocessor does that for us. Okay. So here's that, maybe with a little more, animation, right? So if I say get max of an int function 1, 2, it's going to just swap out the Q's. So let's try to write one of these real quick because there's nothing quite like writing. Let's write a get median function. So consider the function that's already there that's not templatized, okay? And it's there to write and process characters. Let's write an additional one that uses templates, okay? And we'll call both of these from main, and we'll test it out this way, right? That should return B. And if we call the templatized version, and these can both coexist, you can have written this one and leave it there, and then write a template one right below it by copying and pasting and just modifying it, right? And then we can call them individually down below, okay? So let's try that first and get it started. And then we'll see what happens if we try to do this right here, okay? So take a look at program IZ if you like. You're on a quick path in there, okay? The quickest way to write a templatized function is first to write the untemplatized version, which we have done here, right? And then paste it and decide to change stuff. So I'm just going to say template less than type name Q, right? Done. Okay. And now anywhere I see the character, I'm going to put a Q. Okay. Q, Q, oops, Q, Q. Okay. And that's it. And then down below, if I want to call it with integers, it's going to be just like this one. So we can copy paste this here, and we'll use that to get started with. Okay. And I'm going to get rid of that for the moment. The middle of, let's say, 1, 2, 3, 1, 2, 3 is get median int, right? Integer Q type. And then I'll put my 1, 2, 3 in here. Okay. 1, 2, 3. Okay. And hopefully I don't have too many bugs. There we go. Okay. So this is pretty clear because get median it's pretty clear which one to call. Now, if I were to have done this below and try to call a templated version, let's try to just do that with the character thing now. So if I were to say, what if I just say char here, okay, and I run it, it works. So it's going to call one of these things, right? Probably it's calling the templatized version up here. Now, how do I know which one it's calling? Let's just be a little tricky about this. STD, cout, cout. Hi. Okay. I won't even put any NDL after that. Okay. So we can see that we're triggering the templatized one down below. Okay. And in fact, if I now just go ahead and delete, let's see what happens if I comment out the untemplatized one. Okay. Control slash. I don't know if you guys remember that. Control slash will actually do that for you. Okay. And now we're automatically falling back to calling the templatized one. Okay. So it gets a little crazy. Probably you don't want to have one of these and one of these. I would just go with the templated one and let the preprocessor do everything for you. Okay. But that's really all we're doing with those things. We're just kind of copying and pasting information. Okay. And here's our main again, right there. Okay. Questions on that so far? It's kind of our step one.
How does that work if the data is not there yet? Like if we're writing something that's going to encounter different types of data later?
So it has to be able to resolve it at compile time. So let's say you're opening some data from a file and you don't know what kind of data that's going to be. You're still forced to put it in a variable at compile time. So it's going to always kind of know the data type at compile time. Languages like Python are very interesting because you feel like, well, maybe that's what Python's doing, but not really. Python figures it out at runtime. Python has all of this infrastructure where it goes, well, I don't know what type that is, but I have a lot of extra stuff and a lot of more things slow me down. So that's why C++ in languages like it are so much faster in this scenario. So. And some folks might be interested to know, even in Arduino, we'll support templates. So you can like do some pretty crazy things on an Arduino because it's already compiled into the executable. There's no runtime stuff happening to figure out data types and things like that. So maybe the long answer, but fascinating stuff, really. So you can kind of try different permutations on this. And note that we're kind of doing this all inside of one main.cpp file now. We'll talk about the implications of pulling it out of the CPP file. Okay. But it's important with templates to constantly remind yourself it's already done by the time the zeros and ones get created. Okay. So now the cool or maybe confusing, is you can get crazy with this stuff, right? So I can say, well, the data type of the arguments is different than the return type. Okay. So I can say one is an int and one's a float. Okay. So if it turns out that the Q type cannot be forcibly converted on the return into the R type, then we get an error. We get a runtime error. Okay. So it is possible to create some bad situations with these templated functions, right? So we got to write good code, basically. Okay. So, but let's try a midpoint, a templated function. Okay. So we want to specify the argument type and the return type. And notice there's no rules about what order those types should go in. Okay. So we want to watch out for what order we say what when we actually call our functions. So I've called our types here much more clearly so we can kind of tell what they are. Okay. So let's go jump to the solution. But this is, notice what we're doing here. This is not character. This, when we look at the code, is going to say these are character types and the return type is character. So it's a very common misunderstanding when we see multiple templated parameters here, I'll show you, to think they associate with our arguments. We literally have to look at the code to know what they actually mean. Okay, so let me just pull up the program IZ, but I'll let you guys dig into it and I'll put up the solution on that here in just a second. But here's our non-templated thing, right? Character. We want that to be one of our template types, and then we want to force it into some other return type, which means we probably want to force this into the same return type as well. So one of our parameters is going to swap into there, and our other parameter is going to swap into there. Okay. And then down below, you can kind of uncomment this thing here when you're ready. Okay. So let me jump to the solution so you guys have a reference on this, because I know this is kind of crazy stuff, right? But we're like saying template, type name, argument type. Notice I kind of articulated that first, type name, return type. And then I just use those where I want to use them. Okay, so whatever the argument type gets put in front of my args, it's put in from the return type is the mid. Okay, and then we return the mid. So depending on what you choose, you can get some pretty wacky results. Okay, so this one should default to using, actually, I don't know if that one will work without having both functions implemented there. I'll take a look at that in a second. But there's our arg type, comma, return type for the AE. Okay, so those things should work. And int float gives you a surprising result because we are forcing the return type into the float space, right? But if you said int, you would get something different. You get a 2 result on that, I think. Yeah, it's a midpoint. Okay. I think that's the last thing of consequence. So let me look at my, actually, I'll leave you guys with that for now. Let me give you a moment to kind of do that. Get comfortable with that. So reading this code sometimes can be a little confusing. So that's why I don't like the T all the time that people use. So, okay. Questions on that before you press on? Okay. So remember that our compiler is always looking at our use case before it writes this. This stuff is going to be gone by the time the real C++ compiler comes along. It's going to have 3 or 4 different versions of that. Okay. So that's always happening in the background. Okay. Now it's very tempting to write code like this because you can do this in Python, right? It's like, hey, if Q is equal to int, do something, right? But you have to remember that Q is never there in the end. It's like, is int equal to int is what you're actually ending up with once the preprocessor is done, right? If I make Q be an int, it's just a copy paste machine. And now you're asking whether an int is equal to an int, and that's not really valid C++ code. So sometimes all we need to do to debug our template code is just replace it with a type and ask ourselves whether that would make sense, okay? And so we can't, unfortunately, branch like we can in interpreted languages like JavaScript and Python. We can't do those branching based on type, right? We got to actually just keep that out of there. Okay, so now let's look at where it's really powerful. Really, I mean, functions are great to templatize, but classes are really where the real power is. So we want to defer the choice of types, like in vectors, right? We want to defer that to the user. So what if we want to have a vector of integers? What if we want to have a vector of some class that hasn't been invented yet, right? So did you ever wonder how you could have a vector of like people if you're writing a class called people? It's like, huh, that's kind of some interesting magic. Well, it's actually, this is how that actually happens, okay? So vector int, of course, it's going to write that for us, but if I had this class called node, right? And I didn't know what kind of value I want my node to have. Many of you guys remember this from algorithms class. So a lot of times in algorithms class, we'd wave our hands and just say, well, let's just make it, a linked list of integers or a linked list of characters. Well, now we can templatize the class and say, oh, it's a linked list of whatever somebody wants, right? It's got a value, and we could add a pointer here if we want, but I just kind of kept this simple here, okay? So there is our templatized class. Really, really straightforward, okay? Just swap out all of the data types with whatever, wherever we see a Q, okay? And at compile time, we'll know what that's going to be. So a node of int becomes an int everywhere, or a node of char becomes a char everywhere. And we may need two of those, right? So the preprocessor writes two node classes, right? It's sort of going to process or create two node classes or two constructors, two different kinds of data members, etc. Actually, it's two different classes. Sorry, two different classes. One for the node with integer versus the char. Okay. And that's pretty darn cool. Pretty darn cool. So let's think about writing our own array class. So if I had an old-fashioned array, right? This is a little bit of a sneak peek at where we're going. And I wanted to have it be smarter so it knew how big it was. I would say, here's your data and here's how big you are. And now I want that to sort of just be a smart array that knows how big everything is, okay? But we want to support every single type, including types that have never been invented. That's a perfect opportunity to templatize our class. So this will just be an example of one of those things that we could do, okay? So we'll need to store that old-fashioned array in some other data structure. So we'll write that little piece of code, a little bit of dynamic allocation, and eventually we would have to destroy that, but we're not going to really worry about that right now. So here is our smart array. It's going to have some kind of pointer to a dynamic array of integers. So if you remember, int star ptr is kind of what we need to dynamically allocate an array of integers or an array of whatever, right? So int is the type of the pointer, and the size is always going to be an integer value, okay? But here's the array that we're being given. It's a normal array. We're going to copy the data out of that, and then we'll have, let's say, some other methods like print, etc. So that's just our kind of prototype, if you will. So we'll dig into the actual implementation of that, okay? So T can be anything. It can be int, float, bananas, whatever class type we actually want to support, okay? So our constructor needs to allocate that and then remember the size. And so we'll look at that code here in just a second, okay? So here's kind of what the compiler sees. So we call it, we say, hey, I want to create a my array of template type int. So int comes in and we're given an int array. And so this is how we'd actually create an instance of M, right? M is an instance of a my array of type int where it's initialized with this old-fashioned array here, and it's size 3, okay? So we'll rewrite this thing to just have that, okay? So that's what the preprocessor does, okay? It's going to create that flavor for us. And then we'll take a look at the implementation of that here in a second. But that's the basic idea behind templatizing a class. Okay, so here's our constructor. So again, we're going to kind of say, hey, I want an M that's an instance of a smart array that's initially based on or copied from these values of size 3. So that's what comes in to my constructor. Here's my dynamic allocation, right? PTR equals new int. So I'm saying, hey, create an array of integers of size S, right? Remember the size here, and then copy all the data from the old-fashioned one into my private one, okay? And everything just works out very nicely based on the templates, okay? So let's sort of put this one to code here. So consider the myArray class. Try to create an instance in main. Sometimes the hardest part of templates is just knowing how to create an instance of them. And I need a little bit of practice on that too. So we're just going to create an instance, and then we're going to use the existing function calls as examples for how you change that type, okay? So let me help you with that, and then I'll jump back into the solution myself, right? So here's us calling, or so we're going to create an array of data. You can put anything you want in there, okay? Just remember, this is a little gotcha, that this takes one more character than you think. So if you're putting a 26 characters in there, advanced C++ folks, beginners can be forgiven for this. That's got a \0 hiding at the end of it. So we know where the end of it is. And that is going to take you 27 things. So just a heads up on that. It's not the main point, but there's us creating an instance. So try this in main, and you can put integers there, characters or whatever, but the characters are probably the easiest thing to do. And they'll get copied in, and there's our thing. And then we can say ac.print. Okay. And I can also check the size. If I add a dot size method, I could say, what's the size of my particular string, okay? Which is much more like what we see with our regular string class, okay? And it turns out that C++ does provide something that's kind of like this, a templatized smarter array. And we'll see that here in a couple weeks, coming up very soon, actually. Okay. So you can try this with any number of things that can be copied. Now let's just go look at the code one more time here in the solution. Oops, do I have the solution here? Where did I have that? Oh, I don't have it on the screen here. That's annoying. Let's take a look at the implementation of it from the Program IZ link. Okay, so let me jump over there real quick just to show you, right? So some classes cannot be converted, but this class right here, so we're just copying things over, right? There's no changes here to this code. This works regardless of the data type, okay? So as long as the thing that I'm copying from and to supports square brackets, then we're in pretty good shape, right? But we know that we can do this with integers. We know we can do this with floats, right? So this is pretty universal code here, regardless of the type that I'm using, okay? And this is just a trickier way to actually print out something without having square brackets, right? So I'm saying, hey, the pointer address plus some offset address dereference. This is just for fun, quote unquote, fun. Dereference that address plus I, and that gets me to the array position of that, okay? So that's just another way to bypass the whole square bracket thing, right? Which is kind of a handy thing if you don't have support for square brackets, right? Okay. So fun stuff. Main point, just looking at that implementation of the template. Okay, so let's kind of move on, see if we can find another example here. So high level, first keyword, template, less than, greater than, just like we see with vectors and all those things, right? And then our type name, comma, and then another type name, okay? And you get to choose the name of those things, okay? Now, you can and you may see something like this, class T, class RR. It's the exact same thing as type name, so I don't use it. It's just confusing to kind of fill our brains with multiple alternative ways to say the same thing, okay? So I'm going to stick with template and type name since that works for functions and for classes, okay? Okay, so we now kind of have two powerful things. We have our OS stream override, and we have some templatization stuff that we can actually use, okay? So let's just take a look one more time before we kind of move on at what happens when I call a function, right? So I'm calling the function getMax with an int type. It's just a copy paste operation. Find the queue, replace the queue, okay? That's really all that that thing is doing, okay? Same thing for classes. There's an int there, find the queue, replace the queue, okay? It's almost like it's a function argument for types, we're just pouring in one type, okay? Okay, now out of class, we're not going to really torture you with this, but I just wanted to show you we can do it. But generally speaking, we will just keep our templatized classes all together in a .h file, and that's that. We don't do a CPP file because they're not really .h files. They're templatized classes, and the preprocessor is going to take care of all the magic for us. So if you were going to separate it, it gets a little squirrely because your class type needs to be followed by the template and the double colon and all that other stuff. So we're not going to really do that. I don't think you'll see that in anything, but if we do, I'll give you credit for that. I tried to keep it out of any of our quiz questions or anything. Okay. But let's take a look at a swap function, because here's another just a good practice, something that happens all the time, right? How do we write a swap function that's templatized? So this is a really useful thing, right? So the int is pretty much the only thing that needs to be templatized, right? I just want to like swap these two things and be done with it, okay? So there is a swap function that is out there, and it's in the STD namespace. So it might be a good idea to name your swap my swap, possibly, if you do something like this, so you don't get those two things mixed up. But all we're really doing is passing in a pointer to A and a pointer to B. And those pointers could be anything. They could be int pointers, char pointers, foo pointers, node pointers. We don't know, right? So pretty straightforward to just replace those things with our template type. Same thing if we want to use references. So here we have a slightly different swap function that's using the reference structure or the reference technology to swap these values, okay? So again, we can templatize that one very trivially, as you might expect. So let's try to do this real quick. So take a look at our code here, okay? Because we want to actually be able to swap pointers to some class that doesn't exist yet, right? So let's take a look at our foo class. So we have this kind of foo class. It's really just our good old number class. It's got a value in there. And then I have this kind of swap function we want to actually convert. So we want to say template, type name, Q or whatever you want to call it, and then change all of these things over to be Q types, right? From your template type, okay? And then down below, these are just a whole bunch of code that's going to test all of that stuff, okay? So by starters, I think it should all just work because we've done it for integers, right? But when you uncomment this code down here, I would say just templatize your stuff first and then see if you can get that thing working. You can kind of templatize it and then call it from the bottom there. So let me give you a little help on that. So there is kind of our untemplatized version, and there's our templatized one, okay? I always think this is like connective brain tissue. It's like if we understood pointers kinda, and then you start attaching the templates and you can kind of figure out both of those, you're kind of in a better place. Yes, question.
You want three different
Well, it's gonna depend on how it's being called in main, so to speak. So, oh, you mean three different parameters? Oh, yeah, the problem is, so like if this was a float pointer and this was an int pointer, maybe? Is that what you're thinking?
Yeah, so I was thinking what type name, return type.
Oh,
Not returnable.
yeah,
Or at least two different.
yeah, I get what you're saying. Like if this was a float and this was an int, I think we would run into trouble at this point here unless we sort of force type changed our pointers. Yeah, because the way this code, what this is trying to do here requires that these are the same kind of pointers here. Otherwise, I think we would run into, yeah, I think we might run into a little bit of trouble there. But maybe we could do it. That's a good question. I have to think about that. Could we swap two values that were of completely different types? Yeah, possibly. That's entirely possible. Yeah, good question. Come back to that. Okay, so although we won't use it very much, sometimes we don't have to say what type we want if we specify what the default is. So if I say type name t equals int or foo, then in main, I don't really need to say the foo part. I can just say swap. And if it doesn't know, it will guess, and it will guess the default there, which in this case would be foo, okay? I feel like it's already bad enough realizing what's going on. So I tend to not use defaults with my type names too much because for me, I need a little more self-documentation in my code. Okay. But normally we would need to say foo in there. It's kind of like saying vector without a type. You don't really see that too often. And that's probably a good thing. Okay. So small example of using that. So let's kind of apply this in a maybe more real world situation. So we want to build like a generic board game base classes. So we're not going to really do this in tic-tac-toe. Maybe we'll do it in Risk, but the idea is a lot of board games have tokens. Sometimes they're chess pieces, sometimes they're letters on a Scrabble board. So we always have a board, we always have positions on the board. Sometimes it's rectangular. So we want to come up with a way of like deferring what that token really is. Okay. So tic-tac-toe, homework 2, those things are characters, right? But maybe in Battleship, that's something a little more complex. Or maybe if it's Scrabble, I want to know who put that letter there so I know who got those points, right? So when I play Scrabble, we sometimes argue over who put those letters out there because we forget. So here's a kind of an example of our tic-tac-toe, but we're not going to really do tic-tac-toe homework 2 this way. But you might actually be, inspired to think this would be fun, right? So take a look at our 3x3 tic-tac-toe grid, our empty token, our constructors, right? So this is comprised of characters, but maybe we don't want to have characters. Maybe we want to have emojis, and emojis are strings. So that would be a cool thing to do, but maybe we're not sure. So that's a classic thing we might want to templatize there, okay? So, and that thing might have a lot more information than just a character. It might have who put it there, how many points it's worth, who's putting it in check, who knows what kind of things we might want to do there. So that could be really anything there. So we're going to try to convert this game type to templatized. We'll call it token type, but you could call it TT or whatever you want to call it. It's just going to be, what is that thing? Int, char, string, class name, right? We really don't know yet, okay? And then test your function by calling it with char, right? And then you can kind of pull out the char type if you want to try to turn that into a default, right? So set your default token type to char if you like, right? Okay. And we're going to do it out of class. So we're going to just one time torture ourselves with this really large syntax, right? The class name goes here, including its token type, right? That has to be the token type that's in your base prototype, and then implementation over here, okay? So I'm going to give you some solution code because I know this is kind of squirrely. But take a look at the left side here, the before and the after. So see if you can kind of convert this over, okay? So we have our kind of typical thing up here, right? We're going to go replace anywhere we're dealing with our character, right? We don't know. We're going to decide later what that is, right? Constructor, location is still going to be integer, but the thing that we're sort of putting on the board is no longer a character, it's a token, right? Did this particular player win, right? Is it X's or O's, for example, in tic-tac-toe, but that now is represented by a token, not a character. So we've templatized that type. So that's kind of our prototype, the .h equivalent, even though we're just going to do it kind of in one file right there instead of separating it out. And then our constructor, kind of same thing. You kind of get the feeling for it after a while. Oh, I see a character, so I'm going to replace that, right, in our code, right? But I need to fully articulate the class and the template parameter, okay? And I need to restate this above that out of class thing. So it's very wordy, this separation with templates. And we don't have to do this. Again, we could just have done it all in one normal thing. And that's typically what happens. But some people want to know how to separate these things out. Here's the print me. Okay, so we got to add this. We add this, but nothing inside of the print me needs to change. Okay. But notice this thing right here. This used to be a character or an integer or a string, and cout normally knows how to print that. But what if that's now an instance of a class called chess piece, right? Well, how does cout know? Well, we know now how to overload in our class, our token class, the stream operator. So now this little piece of code would not otherwise work. It just literally wouldn't work. There'd be no way to templatize this code. But because we can overload these operators, we can masquerade as a printable character, right? But we're really overloading the stream and printing out a description, queen, queen to queen 5 or whatever, right? Or, Jeff put that J token on the board for tic-tac-toe or something like that, okay? And that's really cool. I just think that's some really awesome stuff, right? Okay. So what we want to do now, once we've kind of templatized the game, is develop a token, right? We haven't developed the token yet. We're just sort of templatizing the class for int, char, string. Now let's develop that token that can be kind of injected into that game class. So this is what we'd like to be able to do, right? We want to create a blank token or a token with a character and 1 point. So I just came up with the idea of some token where there's a character that represents it and how many points it's worth, maybe a Scrabble kind of thing, right? So this is what we would like to actually do, okay? Or it could be, we're playing a Pac-Man game or something, okay? So here is our token, right? It has a character symbol and a value, okay? Constructor and how many points that thing is worth. So with our constructor initializer list, right? So that's kind of our prototype, okay? And it's got our defaults and everything set up there. So we want to be able to have this thing like that, right? We want to create a game with that particular kind of data type poured into it, right? So there is our templatized game class with our new token. And we'll need to overload the stream operator on our token, right? At least. But we haven't had to do anything now to go back to our game class because we had it templatized. So vector is really like this. Like people wrote vector 10 years ago, but we get to use it every day with brand new classes that didn't exist then. And that's what's so cool about this strategy, okay? So let's take a look at what we need to overload, right? So we need some equivalents. Like I want to know whether maybe two symbols are the same. So I want to overload the equal or the equivalence operator in my token class. Maybe a not equals will be handy. Stream operator, okay? So you kind of realize, oh yeah, the more stuff I put in token, the cooler my game becomes because now all of that stuff just works in my game class. I don't even have to change my game class, right? I just make the token class smarter, okay? So here's just some quick peeks at some overloads, right? So there's our, hey, am I the same as the thing that I'm being compared with, right? So if I say if toke equals toke, right, that's what I'm overloading there, which is really cool. There's the not equals, okay, operator not equal, okay. Here's our messy stream operator. So now we can print it out, which is really cool. Very, very handy. Okay. So we're just saying, hey, here's something I want to add to that stream. And I'm just printing this symbol, right? I could have printed symbol, comma, value in parentheses, right? So it's entirely up to you, okay? So our last practice problem, and then we'll wind this up. We'll let you guys get on with what you got to do next. But if you want to tackle this one, we're just going to try to implement that stuff, right? And then we'll print out our game board and see that we can actually kind of augment it in a pretty cool way with this token, okay? So if you take a look at the code real quick, and then I'll jump to the solution so you don't have to watch me stumble around up here. But notice, so there is our token. It's got our equal, it's got our not equal. So all this stuff's already written for us, right? Okay, here's our game class, right? And here's our constructor, right? This is our default constructor. And this could be combined into one constructor, but here's our constructor where we specify what the empty token is, okay? And here's our print me, right? So that is printing out and using the overloaded stream operator for whatever that, if we use our token class there, right? If we call this with the token class, we'll be using our overloaded stream operator, okay? So all we're really trying to do here is kind of get you comfortable with creating those instances. So let me show you that part there, right? So create yourself a token, right? So call it whatever you want, star token, right? Give it some value, some character, and maybe a point value, right? Feed it into your instance creation for your game of type token. Okay. And then you can just call the G4 print me off of that instance, and it should print out whatever that token looks like, which should be a star character. Okay. So what we really have, if you guys remember our silly Mars map that we did in Comp 130, and I was like, hey, we're all going to have an instance of a sample class here, right? And our little rover is going to go around and leave tracks all over the place, right? Well, we could have templatized that class, right? If we knew about templates, and then our Mars map could have been made of samples or integers or whatever we want, right? So that's really what we're doing here is we are templatizing our 3x3 array or 2D array with 3 rows, 3 columns, right? And we can, you know, kind of create all sorts of games that way, okay? So, and this would not work unless we could overload the stream operator. But once we do that, it's kind of magical when all these parts hang together, okay? So here's our constructor, right? So nothing really special there. We just have to remember how to implement it out of class, okay? Constructor, second constructor. This is actually our second constructor, right? Oops. And many of us will have this mistake in our homework too, by the way. I know we're not templatizing homework too, but don't forget to store the empty token because later on, when you come back to check whether somebody has a win or not, if you haven't updated your empty token, you're going to get a wrong answer. Okay, so that's a nasty little bug, just FYI. Okay. And then this is our print me. So, and then our final print me. Again, nothing changed here. Just got to declare that it's tokenized, templatized rather. Okay. And I think we're out, right? So now, if you had done this to your game, you could then use emojis, right? So I think everybody by now knows that emojis are just strings. So if you go to one of these websites and copy paste some emojis and you support a string-based token, then now you can have emojis in your game, right? So all from the benefit of being able to templatize that stuff, okay? And that is it. So our lab today is just to templatize the myAdd function, right? Convert to templatized type, right? I think it's a pretty straightforward one, right? And then I think you just got to call that. And I think the links are all in Canvas. So even though I just have one link here, I should have updated that to the Program IZ link. Okay. And I think, oh yeah, there's a few other things in there too. So you'll see them from our practice problems today. So just see if you can kind of update those things, test them out, and you should be good to go. Okay. So we're just trying to add different data types here. And remember to check which one of these is the arguments and which one is the return value, right? Because you might be surprised which is which. So you got to look at the code to actually figure that out. Okay. All right, I'll leave you with that and let you guys do what you got to do. Send me your links in email, and I will let you know as soon as I know when the Program IZ Pro playgrounds come back. Okay, thanks everybody. Have a great weekend. Stay dry.